Hello guys, this is day number 23 of our daily push-up challenge while solving Putnam problems. This Putnam problem is from the year 1982. 2 more days to go and then we're done with the push-up challenge. But before we read the problem, let's insert some push-up in there. 1, 2, 3, 4, 5. Okay, and like always, let's write our progress here. 5. Okay, the problem reads, evaluate the integral from 0 to infinity of arctan pi x minus arctan x all over x dx. Okay, so one thing that I've noticed is like this whole thing. So let me write it as 1 over x, then the numerator. So instead of writing arctan, let's use the modern notation tan to the minus 1 of pi x minus tan to the minus 1 of x ds. So it looks like a remnant of another integral being evaluated from 1 to pi, right? It's like you have another integral inside the integration of x that you've already evaluated. So to see what I'm talking about, it looks something like integral from 0 to infinity of 1 over x. And the one inside the braces, it's like you're evaluating the arctan of some variable, let's say y. Okay, yx, you're evaluating that from 1 to pi. So it's like there was an integral there before that you already evaluated. Let's continue the push-up. 6, 7, 8, 9, 10. Okay, so the question is, what was this integral beforehand? So in other words, what is the function that when we integrate gives arctan? Or if to replace it simply, what is the derivative of arctan yx? All right, so that is 1 over x. So this whole thing is just the integral from, no, not 0, from 1 to pi of, so the derivative of arctan of x, this of course is with respect to y. You've integrated it with respect to y. So that's y over 1 plus y x squared, right? Because ordinarily, if it's just tan x, arctan x, its derivative will be 1 over 1 plus x squared. But then since you have like x inside, yx inside, then you use the chain rule. And of course, I'm an idiot. The numerator is not y; it should be x, correct? Because when you use the chain rule, when you do the derivative of arctan of yx with respect to y, then x is the constant, right? So x is the one, the numerator. This is of course with respect to dy, and then outside you have dx. Okay. 11, 12, 13, 14, 15. So it looks like we made the problem harder, but not really, because the thing is you can now cancel x here, correct? And then what we can do is maybe we can swap the order of integration. So instead of integrating y first, let's integrate x first from 0 to infinity. So that's already 1 over 1 plus yx squared. We're integrating dx first and then dy. So we swap the order of integration. Did I write 15 or were we already... just to be safe, let's start at 10 again and then up to 20. 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Anyway, so let's write our 20. So like I said, we're integrating with respect to x, right? So this is just, so the integral from 0 to infinity of 1 over 1 plus yx squared. So you can just let yx equals u, okay? And so doing so, you have to introduce a 1 over y coefficient. And then the integral now of 1 over 1 plus u squared will be, of course, arctan to the minus 1 of u, evaluated at, so when x is 0, you set u equals yx. When x is 0, u is still 0. When x is infinite, u is still infinite, okay? And then you have dy. This, of course, is nothing but, so you have arctan of u. When u is infinite, that's just pi over 2. Arctan of 0, that's just, of course, 0. So this whole thing is just pi over 2. Okay, let's finish the push-up. 20, 21, 22, 23, 24, 25. Okay, we're done with the push-up, but we're not yet done with the problem, but I think we're almost there. So this is just pi over 2. We can factor that out. The integral from 1 to pi of 1 over y dy. The integral of 1 over y dy is just, of course, ln of y evaluated from 1 to pi. That is just, of course, pi over 2 ln of, so ln of pi is of course ln of pi, but ln of 1 is just 0. So we are left with ln of pi. So this is like our final answer. And like always, since this is like a definite integral, we can actually ask like a mathematical software to evaluate this for us. So let's put that there, and then let's look at our Math Studio right here. Okay, so let me create a new blank page here. Okay, so let us integrate. We are integrating arctan, so arctan of pi x, and then we are subtracting it by, we're subtracting it by arctan of x, and then the whole thing we divide by x, correct? And then we evaluate that from x starting from 0 to infinity. And then let's close the parenthesis. Let's enter. And that doesn't help us. So here's what we're going to do. We said that our final answer is pi over 2 ln pi. So let's evaluate what that is. So you have pi times ln of pi. And then this whole thing, we divide it by 2. So if this is equal to the number that we got here, then we're done. We're very good. Okay, let's enter. And of course, this is the number. So pi ln pi over 2 is 1.798, which is exactly what you get when you evaluate the entire integration. What that means is our final answer here is correct. Okay, when we evaluated that. Okay, so yeah, so that was straightforward. Again, the trick was to, which was of course very obvious, it's like inviting you to do it, is to realize that there was an integral there before you arrive at this one. I'm sure there are other ways, but yeah, this looks very elegant. But anyway, guys, yeah, this has been day number 23 of our daily push-up challenge while solving a Putnam problem. We have 2 more days to go. I'll see you next time. Thanks for watching, and like always, bye-bye.